here. So now let's design the power supply, flyback power supply that we need. So I am not going to draw the circuitry because the circuitry is same only, and wherever the thing would be required, I am going to draw the components alongside. So let's do first. We need to have to select an input bulk capacitance. The input source here is an AC supply. Obviously, we are going to do a rectifier and then flyback transformer. So suppose if we are having an AC rectified application, the total input bulk capacitor, this should be sized to provide energy from the peak of the minimum input AC line voltage to the minimum allowable voltage. Okay. So due to the transition mode operation, too low of the V bulk selection results in a higher RMS current at the minimum of the input voltage, and it's going to affect our efficiency. And if the V bulk minimum is, that is the minimum allowable voltage, is it's too high, it's going to enlarge the volume of the bulk capacitor. So this equation, we are not taking up any hold up time requirement for an AC line dips or dropouts. We are basically not taking an input bulk capacitance here. That's basically given by formula P naught by an efficiency into 0.5 plus 1 by pi sine inverse V bulk minimum. I'm writing here because okay, yeah, this is the component selection. And this formula is given in the data sheet of the controller only. So I am designing the complete power supply now. So V bulk is equal to P naught by N into 0.5 into 0.5 1 by pi sine inverse V bulk minimum by root of the input minimum, the whole divided by 2 into V input 2V square minus V bulk minimum square into the line frequency. So this formula we are going to choose to find the capacitance value. Okay. And now let's come to the transformer. Let's come now. Suppose the ratio of the transformer I am taking let's say NPS only. I am taking the ratio of the transformer. That's ratio of the primary winding turns to secondary winding turns. And let's say that the maximum of this transformer ratio, it's basically limited by the maximum derated voltage, drain to source voltage of the MOSFET. And if suppose we are saying that delta V clamp is the voltage deviation from the reflected output voltage, so we can either, or it can be either the ripple voltage of the C clamp in an adjustable amplitude modulation, or basically or the voltage overcharge of the capacitor clamp capacitor by the leakage inductance energy when the QH is basically disabled in the LPM. So V out is an output voltage and VF is the forward voltage drop of the secondary rectifier, and we are getting the ratio NPS maximum. This would be the ratio would be what? Voltage drain to source I just mentioned here minus V bulk maximum minus clamp delta V clamp by output voltage plus forward voltage drop. This is the maximum value. The minimum value would be of an NPS, or the ratio would be, it is going to again, so this was limited by maximum derated drain to source voltage of the Q. Okay, here it's going to be derated by again drain to source voltage but of the secondary rectifier. Okay, So this would be equal to V bulk by V, the rectifier voltage that we have taken, whatever we want to, let's put VR only, minus delta V max. So we should know we are taking a basically here a spike here, and this spike should account for additional voltage spike higher than the V bulk maximum divided by the ratio of the NPS when the switch is going to be in high and going to turn off at a non-zero current in the adaptive amplitude modulation mode. So since the high frequency transformer is usually a core loss limited design instead of a saturated limited design, and the minimum duty cycle, that means is going to be very more important, and the lower D minimum is going to increase the core loss at a V bulk. So this constraint creates another limitation on the NPS minimum, and the winding loss distribution between the primary and secondary side of the transformer is going to be the final consideration, and as the NPS is going to increase, the primary RMS current is going to reduce while the secondary RMS current is going to increase. Conversely, if the NPS is going to be decreased, the primary RMS current is going to increase and the secondary RMS current would be decreased. Okay. Now let's take on the primary magnetizing inductance. So let's take the primary winding inductance. So primary magnetizing inductance, you can denote it by, let's say it's in LM. So we have chosen the ratio. Now we can estimate this on the minimum switching frequency at the V bulk minimum and the maximum duty cycle, and the output power at the highest or nominal output voltage, nominal full load current. So the choice of the switching frequency should consider the expected range of the switching frequency as the bulk voltage increases from the minimum to the maximum, and as the load falls from the maximum to the burst mode threshold. Okay, so let's say we have a duty loss to wait for a switch mode transition from the reflected output voltage to zero given. Okay, and we can so we have to basically consider the impact of the full load efficiency and an EMI filter design. So the primary winding turns, let's talk about the primary winding turns. So the turn number on the primary side of the transformer is going to be designed by what? Maximum B, let's say the B max, that's the maximum flux density, and this must be kept lower than the B saturation limit of the magnetic core under the highest peak magnetizing current. Given cross sectional area of the core, geometry, and the higher core temperature. So when it is going to be equal to 0, the IFP is going to be equal to 0 amperes. So like, because we are going to have a soft start or a step up load transient, the peak magnetizing current reaches an IM plus the maximum. Okay, now we can calculate the highest peak magnetizing current. We have to calculate it, and the data sheet says the formula that we are going to use is twice P naught by D max V bulk eta efficiency V CST maximum V CST VCST maximum by VCST OTT or OPP. So the Bmax, it would be equal to Lm, this which we have calculated here, upon NP number of primary turns, cross sectional area of the core AE, and it should be less than below the saturation limit of the magnetic core. Now we have taken AC flux density. So the AC flux density delta B, let's say in my research paper I have drawn an AC flux density by BAC, so that we can know it's an AC flux density or whatever, but let's say I am taking here delta B here. So the AC flux density is going to affect the core loss of the transformer. For the transition mode, this active clamp flyback, the core loss is usually highest at the high line, because since the switching frequency is highest and the duty cycle is the smallest for a given load condition. And the following equation is the delta B calculation. We can basically include the contribution of even the negative magnetization current. Okay, we know there is a Steinmetz equation. I am sorry if I am pronouncing the name wrongly, but we have to put into that equation, including, we are also including the negative magnetizing current. Okay, and we know that V bulk is greater than or equal to number of primary turns VO plus VF. So we are calculating an IM with a bulk V bulk that is divided by the characteristic impedance of the inductance, or rather I should say the primary magnetizing inductance and the lump time related switch node capacitance. So that makes sense. So the expression is derived based on a triangular approximation of the magnetizing current, and is going to consider an IM or the effect over the wide AC line. It's very simple. IM is equal to under root of C capacitance by the magnetizing inductance. It's going to be negative here. It's going to be under root of minus C by into B bulk, and this is negative. Simple. This is an input I, is a power output upon eta upon a V bulk. Again simple. And we have a duty cycle that is going to be the NPS VO plus VF by V bulk plus NPS into VU naught plus VF. We got duty cycle also. What would be the switching frequency? The switching frequency is going to be D square V bulk divided by twice Lm input minus DLm Im plus D V bulk into 0.5 pi under root of an LC. This is the switching frequency. Now we have an Im plus. Here the Im was basically negative side, because we are considering the negative magnetizing current, and the positive magnetizing current would be twice P naught at a full load by eta efficiency Lm into the switching frequency, this switching frequency, plus the negative magnetizing current square under root. And now we are going to get an AC flux density. How we are going to get an AC flux density? AC flux density BAC dot, we are going to let's take delta B equal to Lm of these magnetizing plus with the negative magnetizing current divided by NP into the cross sectional area of the core. So this is how an AC flux density is calculated. Now let's go to the secondary winding turns, which is very simple. We know the ratio, primary secondary, just divide it. Now let's go to an auxiliary winding turns. So let's go to an auxiliary winding turns. So we know that the VDD has to be lower than the maximum rating voltage of the DD pin maximum at the maximum output voltage, and the rectifier forward drop would be the VO max plus VF, and VDD maximum is also limited by the lowest voltage rating of any other devices connected to the VD pin. So we can say the maximum auxiliary winding turns would be VDD, that is at the maximum, by output maximum plus forward voltage into secondary turns. Now the VDD nominal, it should consider the impact of the standby power, and high VDD results in a static loss that is going to increase with the total bias current of the device. A VDD greater than the 13 volt threshold voltage of the survival mode is the sum of the VDD at off and the VDD at PCT at the minimum sustained output voltage, VO minimum. Delta V here represents the voltage difference between the nominal VDD and the survival mode threshold. So a minimum of 3 volts is recommended design margin for delta V, and we now know this is the maximum. Now let's calculate the minimum number of an auxiliary winding. The minimum number of auxiliary winding is what? We have taken a VDD max. Here again we will take VDD off plus VDD PCT plus delta V by VO minimum plus V forward. Again the secondary number of turns have to be multiplied by this, and this would be give the minimum number of auxiliary winding turns. This is going to give the maximum number of auxiliary winding turns. So this must accommodate the highest VDD of, that's what we have done it, threshold also. So let's go to the winding and the magnetic core materials. So we know that besides the choice of an AC flux density, we have to select the materials. As we are going to use the switching frequency 250 kHz, we are going to use a ferrite material 3697, 3C98. Both are basically by the. Okay, so these are the ferrite materials that we should use to exhibit a low core loss density. And if we this is at the full load. And if suppose we want to operate at full load, this is at the for the switching frequency 250 kHz. Suppose we want to operate the converter at 400 kHz, then instead of these four materials, we should basically use a 3F36 core or N49 core we should use, so that we can have a lower core loss density. and we can use other ports also if they have the equivalent or the similar characteristics. And again we are going to use the leads wire both for the primary and secondary windings in order to reduce an RAC winding loss, which is going to cause by the proximity effect and the skin effect of the transformer windings. Now we have to use a clamp capacitor calculation, because now clamp capacitor calculation. Clamp capacitor. Okay, we have to. So basically we are having there are two resonance which are happening. We can either use a primary resonance or we can use a secondary resonance. Okay, and both which approach we are going to take it is going to it's going to affect our design guidance for the clamp capacitance. And if suppose I am going to use main storage capacitor with a large capacitor, or just a second, hold on. Okay, yeah. So in the prime flyback transformer which we am using here, so I am basically using here a MOSFET here. One more MOSFET I am going to use here. Here I am going to use an R C here, one RC again here, and in between we have an inductor here. So I am having, suppose say RCO1, CO1, RCO2, CO2. Now let's come to the clamp capacitor now. So I said that we have basically two kind of approaches, whether we are going to take it a primary resonance or a secondary resonance. So if now suppose I am using this CO1 as the main energy storage capacitor at the output, and if suppose I am going to use this secondary capacitor here, because basically what we have here, MOSFET here, RC here, inductor here, RC here. So this is a main storage energy capacitor with a large capacitance. This is a smaller high frequency decoupling capacitor. Okay, so so during the operation, this is going to resonate with a C clamp during the, it's going to resonate, just a second. Yeah, it's going to resonate with the C clamp during the demagnetization of the magnetizing inductance. So this configuration is going to call a primary resonance active clamp flyback converter. And if suppose if we are going to use this one as a main energy storage capacitor, this is going to have a larger capacitance, and this is now having a smaller than the equivalent capacitance of the C clamp reflected to the secondary side. This is going to make a secondary side active clamp filter. So for and the primary resonance, let's go to the previous scenario where this one is higher. We have a trade-off between the conduction loss and the turning off loss of this MOSFET. When I had just talked of the C clamp, it was basically here an RC snubber. I have talked about the RC snubber here, and this is not QH here. Okay. Okay, now let's take it here. So yeah, so just a second, I just check it. Okay, we don't have time, it will take me time to quickly search. Okay, now I want to finish it actually. Okay, let's do it without seeing it only. So we are having a higher C clamp. Okay, so I said that for the primary resonance, the design trade-off is between the conduction loss and the turn-off switching loss of a transistor. We need to consider, and for a higher C clamp, it results in less. If we are having a higher C clamp, it results in less RMS current flowing through the transformer windings and the switching device, so the conduction loss can be reduced. However, in higher C clamp design, it results the QF turning off before the clamp current occurs. This should be divided. It's not mentioned actually. Somewhere there is the problem, because technically this should be QH and I could not find it's a QH here. I don't know, there must be some typing or something, because they should be QH. Okay, but I'm not going to do it blindly. Okay, so basically the higher C clamp is going to result in the turning off before the clamp current returns to zero. So the condition of not having a zero current switching, it increases the turn off switching loss of QH, and this would be aggravated if the turn off switch of this transistor is not fast enough. Therefore, the C clamp needs to be fine tuned based on the loss attribution. So if the resonance between the LK and the C clamp, what was an LK? Yeah, there is some other schematic actually I am mentioning. So the numberings are basically different here. Let's say it's a leakage. Now I am taking this leakage only, and that would become the magnetizing here. That's a PWM high. Where is the okay. So let's come to the secondary side. So what I was basically looking at, if the resonance between this LK and the C clamp is designed to be completed by the time this QH is turned off, the clamp current should reach close to zero at approximately 3/4 of the resonant period. So now let's talk about the secondary resonance active clamp flyback. And if we are basically adjusting the resonant time with this LK to fulfill the zero current switching, so a large C clamp will not compromise the ZCS. Besides, during the runtime of the low side switch, the small CO1 is partially discharged by the load current at the same time, and after the QL turns off and the resonance begins, the discharge CO1 makes the initial resonance voltage lower than the reflective clamp capacitor voltage across the C clamp, which forces the magnetizing current to be delivered to the output, as so the conduction loss is basically reduced with the less RMS current flowing through the QH and the primary winding. So now let's select the bleed resistor bleed resistor, because here an RC number is, no, this is an R bleed I am taking, not I am taking, this is given actually. So this is always a bleed only, and this bleed is going to discharge the clamp capacitor voltage to the residual voltage during the 1.5 seconds fault delay recovery time, and after the converter recovers from the fault mode, the lower residual reduces the maximum current strength flowing through the switching devices within their respective safe operating areas, even if the output voltage is shorted. So the residual can be determined by the target multiplied with the characteristic impedance between the leakage, inductance and the clamp capacitor, and the shorted we can say I short max is based on the derated maximum pulse current of the QH of the output rectifier, current reflected to the primary side, or whichever is lower. Okay, so now we have to select an output filter. Output filter, the output capacitor of the active clamp flyback. We know that the CO1 of the primary resonance, or if we are taking the CO2 of the secondary resonance, we are going to, in both the cases, whether we are going to choose the primary or secondary resonance is going to be determined by the load step transient response requirement from the no load to the full load transition, and for a target output voltage that's an undershoot with the load step up transient of a delta IO, the minimum bulk output capacitance can be expressed as this. There is a formula that delta I is equal to T upon delta V. I write it. So the CO, that the minimum value of the output capacitance would be delta IO into T response by delta V naught minus delta IO RC. So this is the response time delay from the moment the delta IO is applied to the moment when an ISB falls below the 10 ampere, 10 microampere. Okay, so this response time delay is also going to consist of the time for the secondary regulator to stop driving the optocoupler input, plus the time for an optocoupler output transistor to turn off. So we are having an output filter now. Output filter, we are going to take an LO. It is going to decouple the effect of the CO2 on the resonant period. The sum of the LO impedance or an ESR of the CO2, RCO2, and the CO2 impedance is the minimum switching frequency, which must be higher than the CO1 impedance at the same frequency to force most of the resonant switching resonant current to flow through the CO1. So this is also very long formula that this output filter inductance should be greater than 1 by 2 pi switching frequency, which is the minimum, the whole square into CO1 minus 1 by 2 pi switching frequency minimum, again the whole square. Now we have to take CO2 here minus R times CO2 by 2 pi switching frequency, okay, which is again the minimum. So on lowering the ESR of the CO1 and then RCO1 is going to help to reduce the switching ripple on the output voltage. Another benefit in reducing the conduction loss is that we have reduced the conduction loss of the CO1 for the secondary resonance ACF converter. and but we have the issue that the damping between an L and the CO is weakened, and without proper damping the magnitude of the low frequency resonant ripple between an L on the CO1 and enlarges output ripple. It affects the loop stability and affects the operation of the synchronous rectifier. So the secondary resonance converter is the most vulnerable, since CO1 with a low capacitance significantly weakens the damping, and we use a serial damping network which is going to form an LR. Is a very effective way to minimize the impact, but is going too much damping is going to result in a noticeable conduction loss, and its conduction loss increase, and if we are having a full load, efficiency drop. It would be a full the efficiency at the full load would be dropped, and it's recommended that an LD LR it should be higher than the theoretical strong damping as the okay. So now let's draw a there are only 3 components are left. So now we need a ZVS sensing network. We know that we have a 3 ZVS components to help the depletion MOSFET perform this ZVS operation sensing safely. It's definitely capacitor, resistance and a diode. And at the rising edge of a switch node voltage, the fast dV by dt coupling through the drain to source capacitance of the QS, it generates a charge current flowing into the current circuit loading of the on the QS source pin. So we can have a possible overshoot on both the SWS pin and the gate to source pin, since the gate is tied to the P13 pin, and the SWS pin with an absolute maximum voltage rating of 38 volt, it can handle higher voltage stress on the than the voltage gate to source. So therefore a capacitor between an SWS pin and a ground should be selected properly to prevent the voltage overshoot from damaging the QS gate. Okay, now I take without okay, now let's go to this. So basically now I am coming to the last part, which is basically the drawing of the compensation network, because without it this controller converter won't get designed. I am taking a first order plant characteristic and high switching frequency in an adjustable amplitude modulation. Okay, we are also going to use a active burst mode. That means it's very actually simple. The output coming current here. It's same only. Okay, now I am closing this lecture.